In our simple example here, just to be able to draw something, the spaces x and y were both R2, so that A is given by a 2 by 2 matrix, but also sigma, U and V, as well as V star, are all 2 by 2 matrices. So let's look at the more general case. Let A be a linear operator from Rn into Rm or from Cn into Cm. Let's try to unify both approaches by writing F for the field that could be the real or the complex numbers. So A can be identified with an m by n matrix with real or complex entries. So that now A is in general a rectangular matrix, but one can still split it into a product U, sigma and V star, where U is square and as high as A, sigma is rectangular and have the same shape as A, and V star is again square and as wide as A is. And now the columns of U are just vectors, like we called them U1, U2 and so on before, that play essentially the same role. The rows of V star are the columns of V, are vectors V1, V2 and so on, that have the same meaning as they did have before. And of course you have to take the transpose and possibly complex conjugate to turn them into the rows of V star. And sigma is a diagonal matrix, which sounds a bit funny because in general it's not square, but diagonal matrix in that context means it's supported on the main diagonal, which starts up here and ends where it ends. And the entries are again your singular values that give you your stretching factors for certain directions. And this factorization or decomposition of your original matrix A into a product of three very simple matrices U, sigma and V star is called singular value decomposition, or in short SVD of A. The columns of U again have length 1 and are pairwise orthogonal to each other, which makes this an orthogonal, or in the complex case, unitary matrix. Same is true for V and correspondingly V star. And this is a slightly oddly shaped diagonal matrix. Okay, now let's talk about the rank of A. And let's label this by little r, and of course r cannot be more than n or m. On the other hand, multiplication by an invertible matrix from the left or right doesn't change the rank. So that's why the rank of A and the rank of sigma are the same. So also the rank of sigma is r, but on the other hand the rank of sigma is just the number of pivots in sigma, and that is the number of non-zero little s singular values. So for example, if the rank of your matrix A is 3, then out of these possibly many singular values S1 to Sn, only 3 of them are non-zero, all the others are 0. Of course, we can always reorder little s's, u's, and v's such that S1, S2 up to SR are the non-zero ones. And we could even order them so that S1 is the biggest and then comes S2 and so on. Okay, so we can always assume that this diagonal starts in the top corner with some non-zero values, and then at some point it ends and all the rest is zero. And one important equality that we could already say at this point is that the largest singular value is the operator norm of A. So recall that this length here is the norm of A. We used to say this is the biggest radius of the ellipse or whatever it is on the other side. Okay, and now we could say that this here is the norm of A. And even if you do not reorder your singular values like these, you could say the maximum of your singular values is the norm of A. Okay, very important equation. And maybe we should write the word singular values somewhere, maybe here. Okay, and these u and v vectors will be called singular vectors, and sometimes you say left and right singular vectors. When we write our singular values like this, it seems pretty clear that we pretend or assume they are all real and non-negative. Why is this so clear? I mean, it was kind of clear in our illustration here because we were real anyway and we did some stretchings and no reflections. How is it clear that we can always do that, or we can always assume singular values are greater than equal to 0, in particular real? Well, let's look at the computation of the singular value decomposition and then we will see. And here you do this what mathematicians sometimes do. You say, okay, suppose I already have all the ingredients of u, sigma, and v star so that this equality holds. What properties would they have to have? And then you cut things down up until they can't do any other than the following. Okay, and that's how you find out what u, v, and sigma have to be. So from here it's clear that the adjoint of A can be written as the adjoint of this product, and we know that you have to take the adjoint of every factor and reverse the order. And then let's multiply A and A star, just for fun. So you get u sigma v star times v sigma star u star, and then recall that v and v star are inverse of each other. So this simplifies into u times sigma. Let me write sigma as a matrix. It's not an infinite matrix, I just didn't want to write all the little details. And then sigma star is the next factor and looks like this. So you just take the transpose and possibly complex conjugate. And then comes u star. And of course you know how to multiply diagonal matrices, and you know what complex number times complex number conjugate is. It's the modulus of your number squared. You get that A times A star equals U times the product of sigma and sigma star times U star. Now sigma and sigma star are generally rectangular, but if you multiply them like this, you get something that is square and diagonal, of course. And U star is just U inverse. And this shows that this here is just an eigenvalue, eigenvector decomposition, or you could say a diagonalization of your matrix A star. It shows that u1 up to um are the eigenvectors of your matrix A star, And here on the diagonal you have the eigenvalues of A star. And that's how you get your vectors U, I, and your, well, at least the modulus squares of your singular values, Si, because you have A and you can compute A star, and that's how you do the rest. Now similarly, if you multiply A and A star the other way around, you get pretty much the same diagonal matrix here, and this time your eigenvectors are little v's. So that shows you that in the end your singular values are only determined up to modulus and then squared. Okay, so obviously this will modulus of a complex number and then squared will always give you a real non-negative number, something like, let's say 25. And then, of course, S1 could be 5 times I, which is a number whose modulus is 5, and that squared is 25. Or you could even take something like 3 plus 4 times I, whose modulus is also 5, and that squared is 25. But, I mean, let's not be stupid. Why not take S1 just 5? So we have this freedom here to make life easy for us, then let's make life easy and take the non-negative real number that gives you, when you square it, the 25. Okay, that's why we can always assume that our singular values are real and non-negative, and we know how many of them are positive, and the rest must be 0 then. If you reorder your factorization or your singular value decomposition of A into AV equals U sigma, which is essentially just multiplication from the right by V in this equality here, you can read that out as follows. Okay, and this time let's be a bit more careful with our singular values. So you have S1 up to SR, and then the rest is zeros. Okay, and we're not quite sure where we end, whether it's in the corner or at the right boundary or at the lower boundary of the matrix, but it doesn't matter so much. But from here you get that AV1 equals S1U1, and then the same with 2 and everything up to R, which is the rank of A. And you can still continue, but now because all the singular values are 0, you're going to multiply UI by 0, giving you the 0 vector. And this box here is telling you all about the nature of singular values and singular vectors. So unlike for eigenvalues and eigenvectors, where you have A applied to a certain vector as a multiple of that same vector, but here with singular values and singular vectors, the situation is different, because A takes as an input a vector of length n, and it produces a vector of length m. Because we even allow rectangular matrices here. And okay, well, the rest of the story is very similar, but you have a whole set of input vectors and a whole set of output vectors and some scalars that tell you what A is doing on them. We saw this at the very beginning, actually. Maybe we didn't say much about it, but when you look back here, then here it is. So your input vectors v1 and v2 are so that A applied to them gives you just the other singular vectors times the singular values, right? Here and here. Okay, and this is the 2D baby version of what we have here in this box now. But from this box here you can conclude that vr plus 1 until vn are in the kernel, and actually they span the kernel. And because your v's form an orthonormal basis of Rn or Cn, you just have to take the span of the other v's to get the orthogonal complement of the kernel. And all the outputs that are not 0 are multiples of u1 up to ur and combinations of these. And the orthogonal complement of the image of A is just the span of the other u vectors. And now here and here you recognize two subspaces that are very important in the construction of the Moore-Penrose pseudo-inverse. And that's exactly why the singular value decomposition of A can be very handy to, if you want to write down the Moore-Penrose pseudo-inverse.